My name is Tom Gordon. I'm the Healthcare Innovation Group Leader at Adhesive Research. Um, Today I'm going to be discussing the rapid prototyping of microfluidic devices with pressure-sensitive adhesive tapes. So Adhesive Research has a 25 plus year history of providing tapes to the medical device industry, including in the area of microfluidics. We began with developing tapes for lateral flow immunoassays, so things for pregnancy testing, for infectious disease, as well as for the identification of chemical contaminants. We then moved into the area of microfluidics and devices such as blood glucose test strips, blood coagulation devices, the detection of prostate-specific antigen, as well as forensics and drugs abuse. And we continue to innovate for the future in areas such as continuous glucose monitoring, gene sequencing, PCR testing, and organ-on-a-chip or cell growth types of platforms. And before I get into the rest of the presentation, I'd like to briefly review the types of pressure-sensitive adhesive tapes that are available in the marketplace. So one would be transfer films, in which a single layer of adhesive is placed on a release liner. This can be used to bond two materials together, and this is your best option for forming a very thin channel height with a pressure-sensitive adhesive tape. There are also single-face tapes in which a polyester film or another type of backing can be used to support the tape. These would be bonded or only on one side, and they would have a release liner protecting the adhesive. And then there are double-face tapes in which the carrier has adhesive on either side, which is protected with a release liner. Microfluidic devices are commonly prepared through a process known as soft lithography. It begins with the traditional photolithography approach, in which you take a silicon wafer, you spin coat SU8 or another type of epoxy material onto it, and then through a lithographic mask and UV light, you form your master device. So this type of master device can then be replicated numerous times in the soft lithography process. And that involves essentially casting PDMS onto the surface of the master mold, curing it, and then removing it from the surface. And then applying it to a glass slide surface after plasma treatment. And this is a highly precise fabrication method. However, it requires this microfabrication facility, which is expensive to access or expensive to build, and requires that plasma treatment in order to get good bonding. And altogether, it's costly and time-consuming process. So researchers have developed tape-based approaches to do rapid prototyping of these types of microfluidic devices. And that can begin with the design of an AutoCAD design of your microfluidic channel. That can then be easily cut with a plotter cutter, which is often referred to as xerography, using a razor to cut the shapes of the microfluidic channel, or through laser cutting of a tape into the appropriate microfluidic channels. That tape, that after it's cut to the appropriate microfluidic channels, can then be assembled with a base and a cover to form your microfluidic device, simply with the application of pressure to bond the adhesive. And then finally, once this full device is formed, it can be disinfected or primed in whatever way is necessary prior to the introduction of the biological materials. A recent report from Rothbauer and et al. In Scientific Reports discussed the characterization of 4 biocompatible pressure-sensitive adhesives for this tape-based approach for lab-on-a-chip and organ-on-a-chip systems. And if you look at the approach that they're taking, it uses much lower cost equipment relative to the microfabrication path that I discussed on the previous slide. It can cost $1,000 to $20,000 for one of these home hobby types of plotters, and up to $100,000 for a more professional, more capable instrument. And you can also get into laser cutting with between $20,000 and $150,000 worth of investment. So it's not too hard to get the equipment and not too expensive to get the equipment required to cut these microfluidic channels. And I think even a better advantage is the total time spent between designing the AutoCAD file to producing your microfluidic device and disinfecting it is a total of 1 to 3 hours, which is substantially lower than what is required to access the microfabrication facilities and produce the full device through soft lithography. Other interesting findings are that acrylic-based PSAs were found to have lower vapor and moisture permeability than PDMS, which for certain applications such as organ cell growth is very important. You don't want to have very high moisture permeability. Acrylic adhesives were also found to support cell growth on their own, which is a problem for other types of materials used in microfluidic devices. And then the membranes and scaffolds can be introduced into the device on their own through the use of the PSA tapes, which allows for the support of organ cells and other types of cell growth. I think another major advantage of this type of approach is it allows for the bonding of dissimilar materials. So PET, PDMS, PMMA, COP or COC, all these materials, polycarbonate, polystyrene, can all be bonded using pressure-sensitive adhesive tapes, as well as the membranes and scaffolds, as I mentioned. And that can provide a huge advantage. For instance, I show an example here where polycarbonate can be bonded to polydimethylsiloxane, or PDMS, through the use of a differential adhesive tape, where an acrylic adhesive is designed for the bonding to polycarbonate, a silicone adhesive is used for PDMS. This is something you can't accomplish using that traditional approach. However, there's some very critical aspects of a PSA tape that need to be taken into consideration when you're selecting a tape. The first would be the biocompatibility of the tape. Adhesives can be tested for their accordance with ISO 10993-5 and -10, cytotoxicity, skin irritation, skin sensitization, and that gives you an idea of whether the tape will support or interfere with biological activity. Related to that is the residual content in the adhesive. So after the adhesive is manufactured, it should have low residual content of volatile materials. And I show an example here of R-Care products, acrylic tapes, relative to a competitive tape, showing the low outgassing that we can achieve in our tapes by designing the process to produce them in a way that's going to drive down residuals. And in addition, the uniformity of the tape is very important, particularly for microfluidic devices. Your channel height is essentially defined by the thickness of your tape. So specialized coating equipment is needed to get very uniform thickness of adhesives for this type of application, and repeatable adhesive thickness as well. Another important aspect to consider is moisture resistance. Adhesives should provide a moisture or fluid resistant barrier. Particularly, this is important in multi-channel devices where you do not want fluids to be interchanging between the multiple channels of the device. That also includes, you don't want air or other contaminants from getting inside as well. Autofluorescence is also very important to keep in mind if you're doing an optical type of test. The tape cannot fluoresce excessively in the region of interest. So we show here numerous adhesives produced by Adhesive Research showing that they have relatively low autofluorescence at some common wavelengths of excitation, 485 nanometers and 532 nanometers. And then finally, the cuttability of the tape is very important. So if you're going through either a plotter cutter or other types of cutting, laser cutting approaches to define your channel, the modules of the tape is very important to consider that it's going to cut well, it's not going to smear on the edges, and it's going to make a very well-defined edge for your microfluidic device. And a real advantage of this rapid prototyping using tape approach is that it's also easily scaled. So you can take that same AutoCAD design that was developed for use in laser cutting or the plotter cutter and introduce it right into medical grade converting, in which you would cut the tape roll to roll and wind up a converted roll that has your microfluidic channel already cut into it. That can then be used in a reel-to-reel type of manufacturing environment or reel-to-chip manufacturing environment in which all the required components for the microfluidic device can be added in a reel-to-reel environment. And that is the best approach to do large-scale production of microfluidic devices. And the various options to cut these channels would be things like laser cutting, which I mentioned earlier, as well as rotary die cutting or flatbed die cutting, which can cut the same shapes as produced with these other approaches. Adhesive research provides some really unique technologies in the area of microfluidics. One will be our hydrophilic pressure-sensitive adhesives. So these are really unique products to provide both pressure-sensitive adhesive strength as well as hydrophilicity, which allows for fluid flow and wicking of fluids into the channel. So we provide both a 93049, which is a single-phase tape, and a transfer film 93450 for these types of applications. We also provide high uniformity double-phase spacer tapes to define the channel of a microfluidic device. So these include various different acrylic adhesives, heat sealable adhesives, as well as different thicknesses of carrier that can be used to define your channel height as needed for a particular device. In addition, we offer numerous transfer films at various thicknesses. So these can be silicones, these can be acrylic-based tapes that provide very strong bonding to dissimilar materials, as I mentioned earlier. We also offer products that are optically clear, so they can provide a very clear path for either identifying fluorescent compounds inside the material or looking at fluorophores, or for exciting those materials as well. In conclusion, adhesive tapes provide a low-cost platform for the rapid prototyping of microfluidic devices for a multitude of applications. However, medical-grade tapes must be properly selected, and there's some important characteristics to consider, such as the biocompatibility, the residual content, the thickness and uniformity, the moisture resistance, the autofluorescence of the tape, as well as the cuttability of the material. And these tape-based microfluidics can be easily scaled to high-volume, reel-to-reel processing. Adhesive research provides a lot of value to the customers who partner with us. We provide design flexibility, we provide very fast development capabilities, and it leads to extraordinary outcomes for our customers. And so, our R&D department partners directly with our customers, the engineers who are designing microfluidic devices, so we can provide the ultimate solution that will solve your problem. And at the bottom of this slide is shown some of the manufacturing and production sites that we have, both in Pennsylvania, in Ireland, and we have sales offices in China, and we also recently brought online medical converting in Glen Rock, Pennsylvania as well. Thank you for your time, for being involved in this presentation. I invite you to contact us at Adhesive Research. We'd love to partner with you to solve your problems in microfluidics, and we have a lot of unique products to offer in this area. So thank you.